It's a pleasure to be with you here this morning. We're looking forward, I think Amanda and I and the other Boulder PIs, of having the forum in Colorado next year. And as we said to Greg yesterday, that's the first step in moving the survey headquarters to Colorado as well. So it's step number one. So we look forward to that. 2 years ago, I was the last speaker in the forum, so it's great this year to be the first speaker and to tell you about an entirely new field of cosmology that is being enabled as a result of the new NASA lunar program. And that's a field that we call hydrogen cosmology. We can utilize the neutral hydrogen, which fills the early universe at very early times, and the famous 21 centimeter line that comes, that is radiated from that neutral hydrogen, to uniquely probe a period in the early universe that is currently unobserved. This is what astronomers call the dark ages and the cosmic dawn. This is a very key epoch in the early universe because this is when the first stars and the first galaxies form. Yet we really have no other way of probing this because of the difficulties at other wavelengths. So one aspect of this, though, is because we're looking at such an early time period in the universe, cosmological expansion has stretched the wavelength to meters and tens of meters and frequencies to just a few megahertz to a few tens of megahertz. Those kind of frequency observations are difficult or impossible from the ground because of the ionosphere and also because of radio frequency interference. So these observations need to be done from the moon. And so what I'm going to tell you about today are a couple of mission concepts that NASA has funded this last year that we have completed, one of which is called DAPPER. Let's see, yeah, okay, so we got the pointer here, called DAPPA, which is a small sat in orbit of the moon, and it takes data only when it's above the proven radio quiet Farside. So we'll tell you a little bit about the science that we're going to accomplish with that, and then that will lead to a brief conversation about a Farside array. So let's get right into it. So let me begin by putting this all into perspective. So this image you see on the left-hand side is really the pictorial representation of the evolution of the universe. So Big Bang at the top, today's universe at the bottom as exemplified by the Hubble Ultra Deep Field. CMB is cosmic microwave background. This is our first time when the universe is transparent that we can take some imaging, and this occurs at about 300,000 years after the Big Bang. At this point, the universe has expanded, cooled enough so that the first atoms of neutral hydrogen form, electrons and protons combine. So at this point, the universe is pretty much, at least as far as baryons are concerned, all neutral hydrogen. This is what we call the dark ages because there's no stars yet. At about 500 million years or so after the Big Bang, first stars form as a result of collapse of cores of dark matter and neutral hydrogen, and the first stars turn on. This is called a cosmic dawn. And in the numerical simulation that you see on the right-hand side of the first stars in a cosmological context, when those stars turn on, they emit Lyman alpha ultraviolet light. That ionizes bubbles of the gas around these stars, which you see represented up over here. Eventually, those bubbles overlap. There's enough new stars to turn on, and we get the last phase transition of the universe going from what was an all-neutral hydrogen to an all-ionized hydrogen that we see today. So this makes for a great picture, a great story, but the problem is we don't have the data to support that. So we have data at the CMB. We have data with the Hubble Space Telescope around reionization, but this entire gap in the middle here, the dark ages and the cosmic dawn, we don't yet have data on this important epoch. So how are we going to do that? So once again, we're going to use neutral hydrogen, and this neutral hydrogen in the early universe, there's a global signal that is an all-sky signal that we can use because of the ubiquity of neutral hydrogen. Even a small dipole antenna has the sensitivity to be able to detect this global signal. And that global signal, you see a couple of models of this here. What you're looking at is brightness temperature, or think of this as radio power, measured against the radio background versus frequency. Because we're dealing with a spectral line, namely 21 centimeter, at the top, there's also redshift. So early on is to the right, later on is to the right, early at high redshift is to the left. You'll notice that the global signal has, these two representatives here, have two large spectral troughs, which is characteristic. The cosmic dawn trough is one that coincides with the birth of the first stars. The Lyman alpha actually couples with the hyperfine line of neutral hydrogen, and that drives this deep absorption trough that you see here. Earlier, at lower frequencies and higher redshifts, is another trough that's expected called the dark ages. This is a pure cosmology trough. There are no stars, no galaxies, and it's just due to the relative cooling of the hydrogen versus the radio background. So using Kirchhoff's laws, the hydrogen cools actually faster than the CMB, and that produces an absorption trough. If you have added cooling, that I'll be talking a little bit more about from the hydrogen, that just deepens the trough, like what we see in the red model that you see there. So this last year in March, we had a very exciting potential discovery of the cosmic dawn trough. This is our colleague Judd Bowman and his collaborators published in Nature a possible detection using a very small radio telescope, a blade antenna that you see on the right-hand side in Western Australia. This is a very difficult experiment to do from the ground. And they detected a signal here that you see an absorption trough that is roughly where we expect the cosmic dawn trough to be. But it is, what was surprising, it's about 3 times deeper than what we thought was possible from adiabatic cooling of the gas. So that limit is shown by the cross-hatching that you see here. If real, if confirmed, this requires some new physics. So what is that new physics? So I think we can begin to get a handle on this by actually looking at the dependency of the neutral hydrogen signal that you see here, and I promise you this is the only equation I'll show, but it is a good one. That brightness temperature depends upon that X bar that you see there is the fraction of neutral hydrogen. In green are some of the cosmological parameters. The real drivers here is the ratio TR to TS. TR is the radio background. So if you increase that radio background above the CMB, again, some new physics required here. Say with dark matter decay, lots of models predict that dark matter may decay. That will heat and increase the temperature. Or also new physics, synchrotron radiation from an early generation of direct collapse black holes. So these will be black holes that were formed out of the Big Bang, did not go through supernovae, but early density fluctuations that collapsed. Again, that would be exciting to see both of those. The other possibility is TS. This is called the spin temperature. Think of this for our purposes as the temperature of the neutral hydrogen. If you cool the neutral hydrogen, and this idea of how you would do that has generated literally hundreds of papers since the Nature article was published, of a kind of Rutherford scattering between dark matter and the neutral hydrogen. This is most unexpected, a different kind of characteristics of the dark matter than what was thought to exist before, and would have to be incorporated into models of the early universe. So this is very exciting. And with DAPPER, what we're attempting to do in our spacecraft observations is posing this pretty powerful question for a small sat, and that is, will the observed behavior of the redshifted neutral hydrogen as we go to even lower frequencies redefine the standard cosmological model? Our money plot is this one at the bottom left, which is the spectrum once again. And our two objectives are, number one is to reconfirm the cosmic dawn. And as Keith Taucher presents in his poster, we have some issues that we've looked at with regard to the ground-based observations, not only things like the ionosphere, but also resonances between the ground plane and the antenna that we would eliminate by doing this in space. And then secondly, going to this dark ages trough for the first time, which is only accessible from from space. And any added cooling above the standard model would, once again, give us a handle on that new physics and interaction with the dark ages. This is a challenging observation to make even from space, even from behind the moon, because as you see on the right-hand side, the black model, or the black curve there, represents the foreground that we have to look through, namely the galaxy. And red signal that is there is the 21 centimeter, and that's 4 to 5 orders of magnitude less in brightness. But we're going to utilize something that hasn't been done before, and that is the fact that the foreground is polarized and the 21 centimeter signal is not. That's where the polarimetry comes from in the Dark Ages polarimeter pathfinder. Okay? So just a little bit about the mission overview. We're going to make use of the infrastructure which is being built at the moon. We'll do a ride share as a result of the build out of the Gateway or Artemis. Then we'll use our own propulsion system to descend to lower altitude. We will operate between 17 and 107 megahertz, and the duration of the mission will be about 2 years. The Farside, we've done some electromagnetic modeling. Neil Bassett is going to talk about this, I think, tomorrow, some of the electromagnetic modeling to specify this, what we refer to as the cone of silence behind the moon of where we would operate. You have to go there because, for example, the lower right-hand corner here, you see a spectrum. This is from wind waves. This is actually frequency versus time on the x-axis. So this is real data when wind waves was in the vicinity of the moon. All those horizontal stripes that you see there, that's RFI coming from the Earth. So the Earth remains very bright. Get behind the moon, then that drops to 0. So this is just a schematic of the spacecraft. Just once again to emphasize, it's a small sat. It's 80 centimeters maximum diameter. The instrument is relatively simple. The antennas are thin wire antennas. We're going to deploy them in 3 stages, and we'll use a half wave resonance of the dipoles to actually tune the receiver to our frequencies. So primary resonances for the band between 17 and 38 megahertz, and then secondary and tertiary resonances will allow us to go out to 107 megahertz. So the spacecraft will spin. We also make great use of previous technology which is flown or is flying. We're going to reuse the Themis antenna, and we're also going to make use of the spectrometer in the Fields instrument, which is currently flying on the Parker Solar Probe. So last thing is data processing pipeline. We've spent a better part of a decade working on this because, once again, trying to detect this signal in the presence of a foreground requires sophisticated processing, which we use pattern recognition, training sets, and machine learning. I won't take you through all of these details because I could do an entire hour seminar on this, but let me just show you a couple of highlights here. For example, removing RFI from the spacecraft and the instrument. We have a neural network technique that we have utilized. The signal extraction will make use of the fact, as I mentioned before, that the foreground is polarized and the signal is not. When we then fit all of our systematics here, our best guess on the uncertainties are shown here in the third panel on the right. And then finally, we do a Markov chain Monte Carlo survey of parameter space, and with that we've been able to show that we can differentiate between a standard cosmological model and a model that needs added cooling with dark matter by greater than 5 sigma. Okay? So our summary then is that with this global spectrum, we think we have a potential of investigating new physics in the early universe. So that's Dapper. The next stage is an array on the far side. And this is a study that we are just completing with JPL. Greg Hallinan from Caltech and myself are working on this. This is using a large lander and a rover that we teleoperate to deploy 128 dipoles on the lunar surface to further investigate the early universe and utilize the gateway to transmit the data. Here, this was the featured graphic, the first graphic in a feature story that Science has published just this week in the current issue on lunar observatories. So I'll stop there. Thanks.
Great. We have time for a quick question for Jack.
Ricky wants to ask a question. Ricky, what's your question?
And we've got this mic here. Okay, I'm going to ask a question. I wanted to ask about Dapper.
Yeah.
So it sounds like that's ready to go.
Yes.
And you're waiting for Gateway.
Right.
Can you get a ride on a Earth-based launch vehicle in the meantime, or?
Yeah, I think we're about three years away from the possible launch.
Okay.
We've completed our Phase A study, so we're working with NASA headquarters right now on funding for a start. By then, we'll have some of the initial infrastructure, so there will be some rides that will be possible to the moon.
And are your measurements only taken on the far side?
Yes.
Okay. And but you're orbiting for 2 years, so you get plenty of opportunities.
Yeah, that's right. So in the meantime, we'll also do things like observe the sun when we're above the near side.
Great. Well, it's exciting. Okay, thanks very much. Oh, do you want to ask a quick one?
Yeah, one quick question. Jack, great presentation about the compelling science that can be done from the cone of silence. But that area seems to be under potential great threat with a lot of plans that are happening. What is going to be done to protect this resource of this radio silent area?
Yeah, that's a great question. And one of the reasons we want to do Dapper and get this array on the near side, on the far side of the moon as quickly as possible. But Jake Bleacher and I talked a couple of weeks ago about requirements for the gateway to make sure that it is not leaking a lot of radiation. We're thinking about how to do that. But of course, there's a lot of other infrastructure that will be there. So we need to do these observations sooner rather than later.
Okay, great. Well, thanks again.